Hey, how are you guys? Welcome back to my YouTube channel. Today we'll be dealing with module 2, the testing of material. Right, so we'll see how do we apply the testing of this material, right? So yeah, that is what you're supposed to know. So here we're given, okay, young modulus of elasticity. We always determine young modulus of elasticity within the line proportion. What do they mean about that? Within the line proportion here, before you reach, before this point here, within the limiting proportion part there, right, before proportionality, before you reach the yield point. Yeah, remember I've discussed about that. Then the formulas calculating Young's modulus. We can use the following formulas to calculate Young's modulus if the stress strain graph is given. Stress strain graph. Talking about graph, discussing about its graph. Young's modulus we know is equal to stress over strain. We know that dot 2 there, if the force to change in the length graph is given, right, use this. If we've given force to change, we use the force original length, original area multiplied by the change there, multiplied by the change. They just made like this. Remember the change is equal to force L over area multiplied by E. Then we make this the subject. We'll find that these to be equal. If we make E the subject, then this will give us this. So yeah, so far we know this is in gigapascal, force in Newton. Original, often they have given this in millimeters. Yeah, they will be given in millimeters when you're dealing with graph, millimeters most of the time. So yeah, what I did not capture this. They say note, but I did not capture it accuracy, but we'll see when we're dealing with some problem there. We have a yield stress. Yield stress, we determine the stress where the tensile piece becomes longer, test piece becomes longer very quick. When it's speeding up to becomes long, okay. Then we've given the dot. If the strain graph is given, you read the yield stress of the given value. Okay, you read it on the graph. If the force to change in length graph, yeah, well, we have two graphs. Stress, strain, force, change in length. Like here we'll have force, here we'll have change in length. Is like the graph, as you can see there, we'll have force this side, here we have the change in length, the other one will have stress, here we'll have strain. Yeah, you have to calculate. If you have given this, here you read it on the graph if you have given strain, but if you have given force change in length graph, you have to calculate the yield. You'll calculate. So okay, we shall see this. Okay, the formula to calculate yield is this. Yield point must correspond with the force. I use the yield stress must use the yield force. There's no way you can say yield stress, then incidentally you are using your limiting proportion, the force or what. It must correspond yield point, yield force over original what. Check the importance over original diameter of the test piece there. Yes, Pascal millimeter squared the area. The ultimate stress, we determine the ultimate stress at the highest point. You see, this is at the highest. the highest point there. It's where it occurs. The ultimate is the highest. Determine the ultimate stress at the highest point of the graph. You read it. If the graph is stress strain, if the stress strain graph is given, you read the ultimate stress of the given value. You read it. But if you have given this, you calculate it. If you are given, if the force change to length given you calculate the ultimate. How do we calculate? We use this force. Ultimate must correspond with what? Ultimate force over original force. We'll see this. Ultimate goes with ultimate force. Stress, this is in millimeters squared, as you can check. Stress at fracture. It's where now is tearing. I'm sure fracture is almost there, about to tear. We determine stress at fracture at the end point of the graph. End point, it's always tearing now. There must be, even the area must be fracture, cannot be original. Or it's original. Which one that where the neck? Which that formula? I remember when. Okay, I will discuss. There was where we use. Okay, it's fine. The neck and all. Would remember. Sorry. You see, all of them they're using original. Yes, we're supposed to use original because if you use this fracture, that means already you mean that the diameter, must original, because when you say the fracture obvious it's always tearing up, so it's useless there. We cannot use the fracture. Okay, it's fine. It will be fracture. Stress of the, you see the stress must correspond with the force of the fracture. Original, as you can see there, we're using originals. Calculate the fracture stress. We know this, we know the SI unit, no problem. Then ductility. To determine how ductility the material, we calculate the percentage elongation. In other words, the percentage by which the material becomes long, right? That is the ductility. We have discussed about the ductility. The formula for calculate percentage elongation, that means to elongate, to become large, to increase in length. Percentage elongation is equal to the change in length over original length multiplied by 100. So where you see this thing, it's in millimeter, so no problem. Malleability. To determine malleability of the material, we calculate the percentage by which the cross-sectional area becomes smaller. So the formula for calculating percentage reduction in cross-section area is this: malleability. The percentage reduction in area is this. We also call it another words. It is malleability. The fancy words there. As you can see. Take note, that is malleability. Then here, what do we have again? Ductility is percentage elongation. Those are just fancy words here. Take note, you'll give an original. You must check, or you must have original like that, then the minus final. Do not make a mistake and say final here. But you see, original minus final minus over original multiplied by 100. Reduction in area, we see there. So let's check example 2. Example 2, the following stress strain result are from a tensile test carrying out on a test piece with remember, this is the test piece. If you're given the test piece, this is actually the diameter that we will use to calculate. Is the one that we'll use. Remember, it's for the one that is used on the test piece. And this length, on the length of 70, that is the original length, is the one that will use original length, initial length or original length. So we are given stress versus strain graph or graph. As you can see, we have to draw it given those charts there, given those values, those coordinates, stress over that. So we have to draw the following, then using that information, then we determine all of this. Okay, so let's start by drawing that. I don't know whether this thing will fit, but let me try. So yeah, let's see. We'll have, they say, okay, sorry, okay, but it says without drawing the graph, determine the following here. Okay, it's fine. They said without drawing the graph. It's fine without drawing the graph. So there's yeah, there we use without drawing the graph. So yeah, then some will use the graph on others. So there we don't use the graph. They say without using the graph. So A, we say the limiting proportion. It's when you must know the limiting proportion. It's when the graph is the point on the curve where the value of the stress stay proportional. You must know it's when these things stay proportional. They must stay proportional. Talking about when you take want the limiting proportion, there must be proportionality there. It's when the strain becomes proportional, and then the strain is given by stress over we want to calculate the what is this, the strain, right? Or Young's modulus. It's where Young's modulus limiting proportion, we'll see that our values will become, it's when if you find the Young modulus, they will become constant, the stress over strain. If you pick any value there, let's say I take this value over that, we can test this without using that. If we can say, if you test that, say 20 divided by that 1 comma divided by 20 divided by that. So if we can say 20 divided by 1, remember this SI unit, this is in megapascal, so it's 20 times 10 to the power of 6 divided by that 14286. You'll get 13 what you'll see that values. So you'll get 13 what there, get 13 something 9999 to the power of there, to the power of 10, like this. So let us take this point also. Again, the 40,1 times 10 to the power of 6 divided by 2,8 571 times 10 to the power of minus 4 there. Then what do we the proportion, the length changes the a bit. Then if we go to the other one, 59, I'm just checking something here, 4,2857 there. You'll see the length. Yeah, if you continue like that, you do your things, you'll see how you'll taste this. The repeating proportion, you'll see that up these values of distress becomes more by 20%, and the strain becomes proportional by this. You'll check if you can check here is 20 where it becomes 20, added 10, goes to check 50, close to 60 is like 20 when you round it off. It's like 20, 2 is like 20, 40, 60, 80, right? 8. When you go to here, it's like 8 goes by that. Then you see it goes by 20, 60, 20, 40, 60, 80. This is close to 100 when you round it off. Then 120. But when you round it off, this must be 120. No, it's limited here. Cannot go there. So this area, this region, there at the top, as you can see there. Check here, we have 1, 2. Oh, right. Now here we have that 4, 5. Right, you add again, add 2, add 1. Now this is far. We have added here, it's 1. Come down, we add again 1. Then here we add 2, 2, 1. So is that. You'll see, you must be vigilant. How do you see that? So must ending here. It's there. It's between that region. Check. 420 is like 20, 40. You count by 20 is 20. 59,84 is the same as 60. It's like 2, 4, 6, 8, 10, 12. But now you count it by 20. 20, 40, 60, 80, 100. This is the same as 100 when you route it off. 120. So there. Then there you see, say 100, and now there's no longer a proportionality there. So it's that region, as you can see. Yeah, it's between that region. Therefore, we can say the proportionality limit must be limited here. The proportionality limit, they say the proportional limit is, and the limit is ending here. There's no longer proportionality, as you can see. So the proportionality will be there at 120. You will be there at stress where it is. It's at the stress when it is 120,6 megapascal. Then we have B. We have seen B, take the elastic limit. The elastic limit. So we must check this, the value, the elastic limit. The elastic limit is the limiting stress, the value up which the material stays elastic and will return to its original or shape when the load is removed. It's like when you have the spring elasticity. Let's say we have the spring. If you apply the force there, that direction there, the spring will be enlarged. Let's say it becomes like this. You see it became long. But if you release, the spring must return back to its original form. Right, is what we are talking about there. What is limiting that? The limiting there. Remember, the limiting must just be 4. Limiting proportion is always the following point here. If you exceed this, remember this is a limiting proportion. It's when it's end. Then this is a limiting. Is this B is next to? You must know this is next to limiting proportion point. If you go beyond this, I will never return back to its original form. You must know your graph there. Right, then yeah, this is limiting, sort of like there is limiting to go to that point. You will never return, just the point just before there, which is when the stress layer, you can say, I can call it elastic limit. It's when 200, and so is next is just before the limiting proportion. Then see the modulus of elasticity or modulus of elasticity. We have talked about this. You've said if you have given stress to strain graph, I said this will be this. Remember, I said we'll use this formula, but within the limiting proportion. Remember, if you have your graph like this, within the limiting proportion, I can say there, it's ending here, the limiting proportion. You take any points between the limiting proportion. It's where we have a proportionality. Here we have stress, you have strain. Any points between these two, between the proportionality. Then we know our proportionality. We said our proportionality, we can take any value. Remember, proportionality we said is from this, that region within proportionality. Let me take the middle one, or we can take this. We are fine. It's one and the same thing there. You can say E within there. You can take any value within that. It's up to you guys which one you prefer. I will take that 79.89 times 10 to the power 6. Divide. This goes with what? Goes with this. Do not forget the SI units, megapascal. This is like that. So that is 5,7143. 5,71143 times 10 to the power of minus 4, this power of 6. So then we'll get these to be 139,81 gigapascal. As always, we know that. Then we have now D, A, B, C, D, yield point. Shall I yield? We've discussed about the yield point. You said the yield point, it's when the strain becomes fast. If I remember here, where is that formula? Yield is a stress at the yield point. We say it is they have told the way is that if you have given a stress graph, you say it is given, you read it in the graph of the, where did I read, where is that note? I don't see it. Okay, let us continue, guys. Where we are left there, we want the yield point. Yield point is same like yield stress there. Yield point. Yield point is a point where the strain fast become more while the stress become less. It's when the strain becomes faster, but stress becomes slow or become less. You can say it's when this becomes big, then this becomes less. Up to you there. But yeah, let's check there. But you can check these values, they are close a little bit, but this is too far now. A little bit there, that one is too to see from there. We are checking that we're focusing on strain. It's supposed to be fast. You see now 1, 2, 4 at least is nearby, 5, 7 at least is nearby, 8 at least is nearby, 23 is still far, but this 61 is very far. We said it's when the strain becomes faster or bigger, bigger than the stress, not actual, not bigger. If I say bigger will be wrong. I want to say when it's become fast. You see here it's become fast, it's increasing fast. Here it's at 61, the strain, but when the stress increasing little bit, so it's here, it's between here, then the stress is this one there. So yeah, will be equals to 132.4 megapascal. Just reading there. So what again do we have? We have what is that? We have we nicely given E ultimate strength. Ultimate strength, the highest point in the graph. If you have given the graph, we almost talk about it. Is the highest point. Highest point. It's where we have the maximum stress occurs. The highest point. Where do we have the? Remember, that must be a highest point. The highest point is when you'll have the biggest strength. If you have a graph like this, will be there at the top there. Where do we have a biggest strength than all of them? Let's check. As you can see, this they are very small. It's increasing the strength. Here we have 216, 215, 200. The biggest value is this one. Yes. No, 15. No, here is 16. So that means the biggest value is this one. So it's there. Ultimate is 216.42 megapascal. Pretty simple, just like that. Then F we're given what? The rupture is the last actual strength of the fracture. It's when now everything is when we T things that getting teared there is the last point. It's obviously is even written here. Fracture is the last point there. Given there 195.4. We've given there our fracture there, stress, fracture stress. We just given there, which is 195.74 megapascal. So this is what it is, guys. So yeah, this is what it is, guys. So thank you guys for watching. Stay tuned, else I'll be doing some more of the questions and examples for you guys. So stay tuned and click that notification button so that you'll be notified whenever I post some new videos. Thank you for your time. Right.